Hello everyone, welcome to lecture on 2nd of November, the Tuesday morning lecture online. So what I'm going to do for this lecture is I'm using headset, so I'm hoping that the quality of my voice will be better and the auto subtitles will be with less mistakes. So I will review quickly what I explained in previous lecture because we all had that break and I hope everyone enjoyed it. For those of you that have forgotten some of the concepts that we discussed, so this review will be beneficial. So we were looking at modulation scheme that a Wi-Fi signal is using, and it is known as Ofdm, standing for orthogonal frequency division multiplexing. We discussed about how that differs from conventional or traditional frequency division multiplexing, the FDM, and we looked at some of the benefits that this signal has in general compared to single carrier signal. So one of the main benefits is that the bandwidth is being used a lot more efficient compared to FDM because we don't have to be worried about the guard band. If you remember, I had a piece of paper in my hand demonstrating how exactly the orthogonality can be implemented for OFDM signal. If you are confused or if you have any question or concern about previous lecture, just let me know and I can explain with more details. So then we looked at two more types, the time division multiplexing and how that is different from the frequency division multiplexing in general. So I want you to be very confident and learn this part very well, because when we move forward to look at other protocols that are associated for Internet of Things, I'm going to refer to this part a lot. So I want to make sure that everyone is understanding this part. So we discussed that when we are looking at time division, we are sharing the whole bandwidth in a way that we are giving the whole bandwidth to one user at a time. So that means that we can transmit a bigger amount of data because the whole bandwidth is given to the user. But then there are issues involved in terms of synchronizations because when user 1 is sending signal at the receiver side, user 1 should be extracted. So those are the things that we should be careful when we are designing a system with TDM. And I think I compared that very well with this table with FDM. And we looked at benefits and drawbacks of each of them and what application would be suitable for each of these multiplexing schemes. Then we were looking at, I already said that we looked at the OFDM in contrast with FDM and also TDM. So I assume everyone knows by now that how OFDM signal is generated. If you have any question again, you can ask me during the lecture on Thursday. And we looked at the sync of the signal, how that is generated and how that looks like. I have a video here that you can watch in your time. One thing that I mentioned was the fact that if some part of the signal gets distorted between the transmitter and receiver, how that differs when we are looking at OFDM and when we are looking at FDM. So I probably should put something here. just make sure that when I'm looking at this spectrum, I'm looking at FDM, and this side I'm looking at OFDM. So you can see that OFDM, because we are using multiple carriers, so if something happens to one of these sinks from the transmitter to the receiver, um, it can be compensated and fixed with less complexity and with less cost at the receiver side. But when we are looking at FDM, the example that I said was, if you imagine you have a large truck carrying multiple objects and the truck gets broken. So what happens is that all those objects will be transferred with delay, and it will be more costly to fix that and transfer those, after fixing that big truck. But if you instead use smaller trucks and something happens to only one of them, the rest will go safely, and only one with less complexity and with less cost can be fixed and transmitted. So this was a nice example comparing FDM with OFDM. Um, then we looked at this conclusion page, and we looked at the benefits and some of the characteristics that are involved for Wi-Fi signal. And also I explained that when we are looking at each protocol, particularly in this case Wi-Fi, we should understand that I'm emphasizing on physical layer, but there are other aspects from each layer that are playing roles for Wi-Fi technology to work. So if you are designing an IoT system that is relying on Wi-Fi, um, physical layer, physical connectivity is only one part of that. You have to take care of data link, network transports, section, presentation, application. I'm going to explain this a little bit further. I mean, because I felt that it is useful if I explain it a little bit more. So after the conclusion, which is just a quick review of what we discussed about Wi-Fi, I have this block diagram here. So again, this is looking at transmitter receiver from physical point of view, but I will explain in following slides what do I mean by looking at other layers exactly. So when I'm looking at the whole system from physical angle, I'm looking at a transmitter. So this block with blue dash line is my transmitter. And you can see the first block here is the data source. So this data source can be anything. This can be the email that you are sending. This can be you browsing something on the internet, or just making a call or anything. That data is coming from that application. So then this data is going to be encoded and modulated. And when I was explaining the OFDM, FDM, TDM, and so on, I was looking at the modulation and also any encoding that is involved for creating that signal. So here you can see the modulation and OFDM are in two separate blocks. Sometimes we draw them this way, but sometimes we put them together and we call the whole part as a modulating block or a modulator. So this part can be a lot more complicated than what you can see in this picture, but I try to find the simplest possible picture that is explaining what's happening. I mentioned that anything that gets modulated should be demodulated at the receiver. I'm trying to make that part clear. What do I mean exactly by that? So at this point, at the outside of the blue dash line block, my signal is ready to be transferred. So here we most likely have an antenna. So that antenna is sending the signal, propagating the signal. And then we will have this channel. This channel can be many things. It can be air if I'm sending it wirelessly. So that channel will be the air and everything inside that air. It can be optical cable. It can be any sort of connectivity that we will have, either wired or wireless. So when we are looking at this example, Wi-Fi or 802.11, most of the time we are looking at the wireless connectivity. And whatever happens in the channel, I explained many effects can change the signal during this traveling. And so at the receiver side, the red dash line block is showing the receiver. So I have to inverse the process that is being done on the signal on the transmitter side, and also I have to compensate whatever happened to the signal during travel in my channel. So most of the time, the receiver side is suffering from a lot of complicated processes, which is going to try to fix the signal and extract the signal. For that reason, it's very important to look at complexity of everything. Well, my meeting room, because of the motion sensor, is getting dark, so I have to go and turn on the light. I come back in a second. Sorry about that. It will happen again. So I was explaining that the receiver should extract the signal and inverse the processes that is done in the transmitter. So you can see I have 4 simple blocks here. I have the demodulation for the Ofdm. So whatever I explained about how the signal is generated, and I explained that the orthogonality can be achieved by inverse fast Fourier transform. So that should be also inversed. So in this case here, we are going to use a fast Fourier transform, not the inverse one. So to reverse that process. And when we are looking at the decoding, so decoding means that for security purposes and for a number of other reasons, we have encoding in any transmission. So here we should inverse that and extract the signal that can be used at receiver side. Then there is a process here called signal to noise ratio. That is also important. I might actually refer to this phrase again in the future. So it is important to know what do I mean by that. I mean that how big is signal compared to the noise. So how it is performing when it is traveling through the channel, how the channel is affecting that. Is it very close to the level of the noise? Is the noise becoming mixed up with the signal, or it is very nice and you can determine which one is signal, which one is the noise? So that means analyzing signal to noise ratio. And then we have this part here, which is very interesting. It is called adaptive modulation control. That means that I am continuously checking my system, how it is performing. And you can see that I have a feedback here. So I'm checking that, am I doing good? Am I getting the signal that I'm supposed to get? Am I reversing the process exactly the way that it should be? And a part of that is the synchronization that I explained. So time and frequency should be all matched between the transmitter and receiver. For example, if you're using 2.4 gigahertz and you want to change that to 5 gigahertz Wi-Fi. So that should be done for transmitter and receiver, both of them together. We don't have to be worried about that as a user when we have Wi-Fi modem at home that is being taken care of inside that black box, magic box, and no one would notice what's happening exactly. So someone in the class asked me, what exactly happens when I'm sending an emoji from my phone, or I'm sending a message from using my phone and I'm using Wi-Fi? What exactly happens? So I have a nice slide here, just referring to Wi-Fi particularly. So just imagine your friend is living the other side of the world and you are sending an email using Wi-Fi to your friend. So when you are using your computer or your phone to send an email, you're using a user interface. You're not dealing with bits and signals and stuff. So you are on a very top surface of that stack. And all you are doing is you are typing your message inside your email and you press on the icon for send, and everything else is done. The only thing you should be careful is that you have connection, you have connectivity. All you need is that. Many IoT applications are um, staying on that level. So user doesn't have to look inside what is happening, and many gadgets nowadays are use nice, very simple, easy user interfaces. So the user doesn't have to be worried about even wiring or what is happening under those layers. But when you are designing something, when you are developing something, you should be aware of all the complications and all the integrations between all those layers in order to make a system work. So that user interface is taking your input, and your input is just typing and clicking for the email. Then everything has to go through a process which I will explain in the next slide, and at some stage will be converted to electromagnetic signal or wave, and then with wire or wirelessly can be transferred. So when it is transferring, in this case, it is going in a channel that is air, and you can imagine what kind of reflections, observations, and all those phenomena that can happen to a signal. All of those might happen to the signal from the transmitter to the receiver side. By the time that is being received, the signal has some changes, needs to fix here and there, but it should be good enough to be discovered by the other person. So again, under layer system is taking care of that, and it is sending it back as a signal that can be converted back to something that your user interface can bring it up and display it as an email in your computer, in your laptop, in your phone. So again, as a user, you don't have to be worried about anything. You don't have to deal with any compensation, anything. But as a designer, yes, you should be aware of all the complications, all the interconnections and integrations between the layers to make that happen. So in lab, we are going to use a new processor that has capability of connecting to Wi-Fi, and also it has Bluetooth connectivity. So that will give you very nice sense of how very simple, easy Wi-Fi based IoT or Bluetooth based IoT can be implemented. Um, so let's take a quick look what happens between these layers and how they are integrated, they work together. Many of these layers are far away from my expert areas. So if you have any question, if you have any concern, you feel free to Google it yourself. And I assume because of the type of the degree that you are doing, in many cases you will be a lot more expert than me. So we start from application layer. The application layer will be exactly the thing that is the user is interfering. The user sees and feels what is it doing. So that would be the email itself from Windows or Android or any operation system that we are using. So that will be the email. And then that email is going to become a kind of like a package. It is called FTP in some cases, and there are many other aspects that they kind of attach to that file to make it like a package that presentation layer takes care of it. To be honest, I don't know the details. I had a search myself, but it seems, as I said, far from my expert area. So if you're interested, you can go and look at it yourself. Then we have something called section layer or season layer. Then that package becomes like a something called API, and that API is going to be managed by section layer in a way that is going to look at things that are associated. For example, is that going to be operated on Windows, or is that going to be operated based on Linux, or a very lot more close to the computer level. So if you look at the API, you wouldn't see the email that you have sent. You wouldn't see the text that you have sent in the email. It is converted a lot more closer to machine language. Then transport layer is going to look at the connectivity. It's going to look at that as a package, a parcel that is going to be transferred. Now, that is going to have information about the place that you have sent, the computer that you have used to send that email, and so on. And each of these layers, they have their own security aspects, safety aspects, and they attach a little bit to the original data. And the package, when it is moving from layer to layer, it always has some adds on to that. Just because it needs to be converted in a form that can be transferred and can be discovered back at the receiver side. Then we are looking at network layer, which is going to be your expertise. We have packets, we have IGMPs, and a lot of other stuff that are attached to that packet that is created with only one email that you're sending. Then we will look at PPP in data link, and that means that that package is known as a frame now. And that frame is might include multiple of those IGMPs, and they are kind of packed together in order to be just sent. Then that's my favorite layer, physical layer. So here we are converting everything to bits, zeros and ones, and then that 0 and 1 is going to be converted to signals. So the signals is nothing other than having the voltage or not having a voltage, having current or not having the current. And then that can be sent by electromagnetic wave with antenna. So this is exactly what happens when you are sending one a small email. Again, from user point of view, you wouldn't notice what is the process, what is happening. You don't have to do anything. You just click on the send and the email is sent. And when you have an email, you just click on that, opens up, and you see that text form. But as a designer, as someone that is maintaining that system, you should be aware of all those integrations. So that's what happens between all those layers. I have this conclusion and lots of links. If you want to look at them, you can look at each of those. There are nice documents, and if I'm not mistaken, there is also a video somewhere here. So that's that will complete the section for Wi-Fi. I'm going to move to Bluetooth. I start explaining the Bluetooth, and I will stop at some point and I will continue in the lecture on Thursday. I just check the time. I don't have time here. Okay, I don't want to exceed 1 hour time, but it is fine for now. Okay, the next protocol that we are going to look at is Bluetooth. Again, another popular technology that many people are using, and many gadgets are using Bluetooth connectivity. Many people have things that are connected with Bluetooth. Sometimes we just overlook the advantages of this technology and how exactly it works. So it is important to know, and I'm hoping that everyone can get hands on the device that we have in lab for Bluetooth connectivity and try very simple program using Bluetooth. We probably will start by only turning on or off one light with Bluetooth in a way that we will have um, an app form a program on our phone, and then we can send one bit to turn on the LED or turning it off. That is the simplest form of Bluetooth connectivity that I'm hoping that we can see it in lab this week. So here in this slide, I have some history. Let me zoom it in. This slide will be available on Brightspace. So Bluetooth came along in 90s, back when people used Nokia. Anyone had Nokia? Some of you might remember that Nokia model. Everyone was very excited about Bluetooth. It felt like another magic. After phones came, mobile phones came, Bluetooth was just another magical feature added to phone. The revolution was nice and gave opportunities for companies, for developers to make benefit of this simple technology that can make everything more advanced. This diagram here is looking at that revolution, how exactly that Bluetooth changed things around us. So mobile phone first got enhanced by Bluetooth and people started to use it and enjoyed it. Then other gadgets, other technologies started to have Bluetooth: printers, computers, keyboards, mouse, cameras, and many other gadgets. Nowadays, many people have headsets that don't use wire like mine, so they are using Bluetooth. Smartwatch is another one that is using, and so on. Tablets and almost everything, even TV at home, has Bluetooth. So you can see how that affected many electronic devices during this time. For that reason, it is very important that we try that in lab to see how exactly that technology is working. I'm going to look at the signal for Bluetooth, how that is generated and how it is working. So let's look at the logo. This is the logo. So the name is funny. I remember myself when I heard Bluetooth for the first time, I was thinking, why Bluetooth? Why it's not red tooth or pink tooth or black tooth? Why it is Bluetooth? What's the story with that? So the logo is taken from 2 letters of H and B. Um, and it seems that based on history, your old uh, Danish kings, and they kind of joined together, and as a result of that agreement or working in join, so they combined their names together and they came up with that kind of sign. So Bluetooth took that idea because it's a nice idea to make connections and join. And the initial idea of using Bluetooth for enabling gadgets was to pair them together. And this pairing, I'm going to explain how exactly that is done and what different types of pairing we have. So the logo is taken from that story. So Bluetooth on your phone is just like that group. In fact, uniting devices from different manufacturing and with different purposes, like computers from Apple and from Microsoft is Bluetooth technology at all. So any any gadget, any technology, any electronic device that has Bluetooth can connect to another one. That's a good thing because they don't have to be worried about anything else. If you buy something from China or if you buy something from Brazil, it's going to work if it has Bluetooth here in Ireland. So that's kind of bringing everything together and making sure that they work together nicely. It's a nice way of connecting things together. There are limitations and challenges involved, which I'm going to explain further. So I'm going to leave you with watching this video here. I assume by clicking that it will open, but I am going to open here. So I leave everyone for watching that, and I will continue explaining Bluetooth on Thursday when I see you all in the class. So I'm just playing this. If the voice doesn't play here, you can play it on your computer yourself. Sorry, I forgot to turn on the subtitle, so I'm going to play that all over again.
talking on the phone through a wireless headset. And recently, you may have come across the term Bluetooth Low Energy, or BLE for short. So, is this the same Bluetooth we use for streaming audio, or is it different? This can be really confusing, but it doesn't have to be. Hi, my name is Mohammady, and in this video, I'll go over the basics of BLE. We'll also talk about the differences between BLE and the Bluetooth we use for streaming audio, or what's referred to as Bluetooth Classic. Then we'll also talk about some of the applications of BLE. So what is BLE? Well, BLE is a low-power wireless technology used for connecting devices with each other. And the key term here is low power. And what this means is that BLE is targeted more towards applications that need to consume less power and may need to run on batteries for longer periods of time, months or even years. BLE was introduced back in 2010 as part of the Bluetooth 4.0 spec. It is not an upgrade to the original Bluetooth, but rather it's a new technology that utilizes the Bluetooth brand, but focuses more on the Internet of Things or IoT applications, where small amounts of data are transferred at lower speeds. BLE operates in the 2.4 GHz ISM band, which is the same spectrum that's used by Bluetooth Classic, the original Bluetooth, and Wi-Fi, as well as some other technologies such as Zigbee. We're more familiar with the Bluetooth that we use for streaming audio, and that kind of Bluetooth is referred to as Bluetooth Classic. Now, one important thing to note is that Bluetooth Classic is not compatible with BLE. So, two devices, a BLE device, cannot communicate directly with a Bluetooth Classic device. So, for example, your smartwatch cannot talk directly to your wireless headphones, but rather some devices implement both BLE and Bluetooth Classic and allow talking to these devices independently. So, what are some of the applications of BLE? Well, some of the most common ones include home automation applications, such as a smart door lock, a smart appliance, or in your lighting system. Another application would be in fitness devices, such as wearables and trackers and pedometers. And one other interesting application is in indoor location technology, where GPS may not be feasible. And last but not least, in medical devices and personal health devices. And now with the recent release of Bluetooth 5 and Bluetooth Mesh, BLE has more feasible applications, especially when it comes to home automation and industrial applications. In BLE, there are two kinds of devices. You have a central device and a peripheral device. The central device is usually the more capable device in terms of CPU power or memory or battery capacity, whereas the peripheral device is much more resource constrained, especially when it comes to battery. Now, BLE is an asymmetric technology, and what this means is that much of the heavy lifting and the processing responsibility is put on the central device versus on the peripheral, which actually allows the peripheral device to sleep for longer periods of time, turn off the radio, and consume less power. So it may be obvious now, but really what makes BLE so special, and what are some of the benefits of using BLE? Well, there are a few major ones that I can think of. First, lower power consumption. Even when you compare it to other low-power technologies, BLE is one of the lowest power consumption technologies out there. Second is the free cost to accessing the official specification documents. Some other technologies, you may have to become part of a group and pay fees to access their documents. With BLE, it's free. The third benefit that I can think of is the lower module and chipset costs. And with BLE chipsets and modules, the prices are going down very rapidly. The fourth benefit, and probably the most important one, is the existence of BLE in most smartphones in the market, which really gives it a huge advantage over other technologies out there. The way that BLE achieves its optimized and low power consumption is by turning off the radio as much as possible and sending small amounts of data over low transfer speeds. So, for example, applications such as video streaming or high-quality audio streaming or transferring large amounts of data are not really suitable for BLE, but rather it's meant for transferring data from small devices such as sensors to a smartphone. So what can we expect in terms of range between two BLE devices? Well, the range typically goes up to 50 meters or about 150 feet. That's line of sight. Whereas when you have obstacles and walls in between the devices, the range can go down significantly, probably to several meters or even several feet. However, when utilizing the long range feature of Bluetooth 5, the range can go up pretty significantly, even up to 800 meters line of sight. Now, what are some of the factors that can limit the range between two BLE devices? There are three of the most important factors include the surrounding environment around the BLE devices. The second one is the antenna design of the device, and the third being the orientation of the devices that are talking to each other, which really is the effect of the antenna and its orientation. Now let's talk about the speed of BLE, and what can you expect in terms of speed between two BLE devices. Well, there's two important concepts to understand. There's one called the raw data rate, and the other one is the application data rate. The raw data rate is simply the rate at which the radio transmits the data over the air, and it varies depending on the version of Bluetooth that you're using. So, for example, if you're using Bluetooth 4.2, then the raw data rate is set at 1 megabits per second. However, if you're using Bluetooth 5 and later, then the raw data rate can vary, and there are different options there. You can either use the 1 megabits per second, which is the original Bluetooth low energy data rate, or it can go up to 2 megabits per second when utilizing the higher speed feature of Bluetooth 5. And when you use the long range feature of Bluetooth 5, then the speed and the data rate goes down to 500 kilobits per second or even down to 125 kilobits per second. Now that's in terms of the raw data rate, but what about what you can expect in terms of your application data rate and how much data you can actually utilize at the application layer? Well, that gets reduced, and that's due to the packet overhead and some gaps in between transmitting some of the packets. So what you can expect in terms of application data rate, for example, when you use the 2 megabits per second, you can achieve up to 1.4 megabits per second of data rate. In the upcoming videos, we'll talk about BLE in much more detail. We'll cover topics such as advertisements, connections, services and characteristics, BLE security, and Bluetooth mesh. To learn more about Elysis, provider of the world's most advanced Bluetooth analyzers.
Okay, I'm hoping that everyone watched that video. I will explain how BLE differs from normal Bluetooth or conventional Bluetooth. And just to mention that it is most likely that we are going to look at BLE or Bluetooth low energy in lab. So as you heard from this video, um, the range will be a little bit limited, but the good advantage is that the energy consumption is very minimal. I also put this link for this video itself in the description of that video, uh, referring to the page that you can watch it again. So I see you guys on Thursday. Thank you very much. Bye bye.